Hello, my name is Tom Willemain. I'm one of the founders, along with Charlie Smart and Dr. Nelson Hartunian of Smart Software. Today we're going to be talking about regression analysis for forecasting, a specialized, more advanced technique that some of our customers use to improve the accuracy of their forecasts. Now, if you're not using regression analysis, you're probably using something called a time series method or an extrapolative method. And the difference is the time series methods are simpler and faster, but not necessarily more accurate. The regression methods can be, but also are not necessarily more accurate. So we'll see how they're used and what would make them a good choice. So let me sketch out a typical forecasting problem. There will be some variable of interest. Maybe it's sales. And we have a record of that over time. So we have a record, say, of demand for a product over time. And the data may look something like this. So it's very random looking. And the time series methods are aiming at a very simple description of this. They're trying to understand where's the middle of that noise. So they're, for instance, trying to do something like this, and then maybe making a forecast like that. And those methods consider all this zigging and zagging to be untouchable randomness. It's unexplainable. It's all the forces in the universe working on the sales. And those are just nuisance noise that has to be averaged out by the time series method. If you're taking a regression approach, though, you look at those bumps differently and you say, what if they are in fact not totally random, but at least partially forecastable? So instead of being a nuisance, there's actually information in the going up and the going down. That's the starting point mentally for why you would try to do a regression analysis. And the key step is to be able to use your substantive knowledge of your problem to nominate for consideration some extra variable, an additional variable that would explain some of that zigging and zagging, some of the randomness. So it's not really random. It's explainable if you bring more information into the problem. So you can see that that's more expensive because you need another variable, and you have to get the record, make sure it's accurate, and then find a way to use it. But if you can find another variable that is predictive of what looks like random noise, then you get a much deeper understanding of the problem, and you can make more accurate forecasts. Whether you can do that or not depends on whether data are available, whether you can use your subject matter expertise to find that variable. So what we will do instead of this picture is make a somewhat different picture. We will try to find another variable which is related to sales. So maybe it's sales and maybe it's, say, temperature. Maybe you're selling something like ice cream, and when it's hot, you have more sales, and when it's cold, you have fewer sales. So now, each point in this time series becomes a dot in this graph, because at a certain day, there's a temperature and there's a sales level. And by looking at two time series and making this sort of a plot, we get what's known as a scatter plot, relating observed values of temperature to observed values of sales. And if you see a picture like this, then you've got something. Then you have leverage to use a regression model to seize this information and refine the forecast of sales, because there's, besides all the forces in the universe that are affecting the level of sales, there's one in particular which may be powerful and knowable and exploitable. So that's the approach we take to regression analysis, and what we'll do with the regression model is say, Here is an approximation to that relationship. So if you give me a particular temperature, I come up to this curve and I can read off a particular projected sales value. So we need to find this line, and then we can exploit that relationship. And if we're just looking back at history and we want to explain to ourselves when is sales higher, when is sales lower, and how does temperature affect that, this picture is the answer. If we want to go further and forecast sales, then the regression approach puts an extra burden on us. Here, with this picture, the time series approach, we can find some way to extrapolate or extend this orange curve. Maybe we're going to make a flat forecast based on the current estimate of where the sales level is. Here, to make a forecast of sales, we have to have a forecast of temperature. And that's turning a single forecast problem into a double forecast problem. But if temperature is related to sales, and if temperature is itself forecastable, then a regression approach can improve the accuracy of your forecast of sales. And what will follow now is some more technical stuff about how you find this line and the three types of regression models that are commonly used in business. One is called autoregression, which is a special case where this second variable is actually just old values of the thing you're trying to forecast. So you might forecast sales next month from sales this month. So that gets rid of the problem of having to find two variables and to forecast the second one because you're just using known values of the first one. That's autoregression. The second of the three alternative ways to use regression is called a causal model. In this case, for instance, we believe that the temperature changes have a direct influence on the sales. They cause changes in the sales. And then there's a third, which is a variant of that, where this variable, the one we're predicting from, is not the same as this one, but it is a leading indicator, meaning that the values of this other variable in the past, not forecasted but already known, can be used to forecast sales. So that too is a way of avoiding the double forecasting problem. So we'll talk in a minute about how you get these lines estimated and about the particular technical details of autoregression, causal models, and predicting from leading indicators.